Hey everyone, and welcome back to part 8 of our Units and Measurements series. Today, we are getting practical. We're moving beyond just the theory of units and diving into the actual instruments we use to measure them, the precision they give us, and the absolute must-know rules to get the right answer. You know, mastering this stuff is all about avoiding those simple, silly mistakes on your NEET exam that can really cost you. All right, let's jump right in. So let's kick things off with a question. Say you measure a table, and you write down 4.700 meters. Do those last two zeros really matter? Well, the answer is a huge yes, and it's all about precision. See, the number of digits you write down tells a story about the tool you used. A simple 4.7 meters? That might be from a regular tape measure. But 4.700 meters? Whoa, that suggests you used a much more precise instrument. Understanding why those zeros matter is exactly what helps you pick the right answer when your options are just a decimal place apart. Okay, here's our game plan for today. We're going to start with the why we even need standards in the first place. Then we'll get into the real language of precision, connecting the numbers you see to the instruments you use, like Vernier calipers and screw gauges. After that, we'll unlock a really powerful tool called dimensional analysis to check if your formulas even make sense. And finally, we'll wrap it all up with some solid strategies for the exam. So first things first, why are we so obsessed with rules for measurement? Well, honestly, without a shared standard, science would just be complete chaos. Imagine a measurement from one lab being totally meaningless in another. Let's see why this foundation is so important. Think about it this way. At its core, measurement is just a comparison. And for that comparison to mean anything, whether you're in a lab in Mumbai or one in Boston, we all have to agree on what we're comparing it to. That's exactly what the International System of Units, the SI system, does for us. It makes sure that a meter is a meter and a kilogram is a kilogram absolutely everywhere. So we've got our standard units. Great. But a measurement is so much more than just a number and a unit. It also has to communicate how precise it is. And now we're going to learn the language that does exactly that. A language that's dictated by your measuring instrument. This is the language of significant figures. So what are they, really? Well, significant figures are basically all the digits you can trust in a measurement, plus one final estimated digit. And here's the key connection to your lab work. That last uncertain digit comes from the least count of your instrument. For a simple ruler, that might be a millimeter. For a Vernier caliper, maybe 0.1 millimeters. And for a screw gauge, it could be as tiny as 0.01 millimeters. Significant figures are just our way of writing down that precision. Let's quickly break down the rules. They're actually pretty simple. All non-zero digits, they always count. Any zeros that are sandwiched between them, they count too. Zeros at the beginning are just placeholders, so you can ignore them. Now here's the one that gets people. Zeros at the end only count if you see a decimal point in the number. That little dot is a signal that tells you, hey, this measurement is super precise. Writing 3.500 centimeters tells the world your instrument was accurate right down to the thousandth of a centimeter. So let's try one out. Take the number 0.06900. How many significant figures do we have? Well, the first two zeros are leading zeros, so we ignore them. The 6 and the 9 are non-zero, so they definitely count. And the last two zeros? They're at the end, and there's a decimal point, so they count too. That gives us a total of 4 significant figures. A measurement like 0.06900 centimeters is something you'd get from a high-precision tool like a screw gauge, not your everyday ruler. Okay, listen up, because this is a huge one, and it's a classic exam trap. When you multiply or divide measurements, your final answer is limited by the number with the fewest total significant figures. But, and this is a big but, when you add or subtract, you only care about the number of decimal places. These two rules are not the same. You have to burn this difference into your brain because it will absolutely save you marks. Let's see this in action. Imagine a question asks for the total mass of 3 objects you've measured. The first, 436.32 grams, maybe from a good digital balance. The second, 227.2 grams, from a less precise one. And the third, 0.301 grams, from a super sensitive one. Since we're adding, we have to look for the least number of decimal places. That's just one decimal place, from the 227.2. So even though your calculator spits out 663.821, you have to round your final answer to one decimal place, which is 663.8. Remember, your result can only be as good as your least precise measurement. Okay, so we've nailed how to take a measurement and report it correctly. Now let's add a kind of physics superpower to our toolkit. It's called dimensional analysis, and it lets you check if an equation is even valid before you plug in a single number. It's like a logic check for your formulas. This right here is the heart of it all. It's called the principle of homogeneity of dimensions. And honestly, it's just a fancy way of saying you can't add apples and oranges. In physics, every single term that you add or subtract in an equation has to have the same fundamental dimensions. You can add a length to another length, sure, but you can never ever add a length to a time. Let's put this principle to the test with a famous equation of motion. Is it dimensionally correct? Let's check each piece. Displacement, s, well, that has the dimension of length, or L. The ut term is velocity, which is Lt-1, multiplied by time, t. The t's cancel out, leaving just L. And what about half at squared? That's acceleration, Lt-2, times time squared, t squared. Again, the t's cancel and we're left with L. See? Every term has the dimension of length. The equation holds up. Now here is another crucial point. Anything that's a power, or anything that goes inside a function like sine, cosine, or an exponential, must be a pure number. It has to be dimensionless. Why? Because these functions work on ratios, not on physical things. You can't raise e to the power of 5 kilograms, and you can't take the sine of 10 meters. It just doesn't make sense. All right, so far we've just used dimensions to check work that's already been done. But now it's time to level up. We can actually use the same logic to build formulas from the ground up, starting with just an idea of which physical quantities are involved. This 4-step process is an amazing problem-solving tool. Let's say you're in an exam and you completely blank on the formula for a pendulum. If you can just remember that the time period depends on the length, mass, and gravity, you can set up a relationship with unknown powers. By forcing the dimensions on both sides of the equation to match, you can actually solve for those powers and rebuild the formula. It's like having a logical safety net. But let's be real, this method isn't magic. Dimensional analysis has its limits. It can't figure out numerical constants like 2 pi. It has trouble with equations that have plus or minus signs. And it's totally blind when it comes to functions like sine or exponentials. So think of it as a fantastic tool for checking your work and for simple relationships, but not for deriving every single formula in your textbook. Okay, let's bring it all home. How does mastering all of this, the practical measurements and the theoretical checks, actually help you ace the NEET exam? Here's the bottom line. NEET questions are designed to test both of these skills. You might get a question with a diagram of a Vernier scale and have to figure out the reading. That's a practical skill. Then the very next question might ask you to use that reading in a calculation where you have to apply the rules of significant figures. That's a theoretical skill. These questions are put there to catch careless mistakes. If you master these fundamentals, you're protecting yourself from losing those easy, crucial marks. So just remember this, precision in your practice is the very first step to getting that perfect score on your exam paper. So what's the one rule from today that you're going to practice first? Make that your next step. Keep up the hard work, and I'll see you in the next part.